I will be talking about 2,6 diluted magnetic semiconductors for spintronic research. And the outline of my talk is following. First, motivation for research or telluride nanostructures. Then I'll show you one slide on quantum dot and two about the nanowires produced by bottom-up approach. And the main part of my talk will be devoted to the two-dimensional structures made of 2,6s. And first, I'll show you results on the Grossen studies, which demonstrated that it is possible to improve mobility of two-dimensional electron gas in the structure by setting the new world record in mobility of wide gap 2,6 tellurides, and also the first observation of fractional quantum Hall effect in both non-magnetic and magnetic telluride nanostructures. And then I will proceed to show you some application of those structures already published. First, demonstration of spin polarization of 4/3 and 5/3 fractional quantum Hall states, observation of enhancement of the spin gap in fully occupied two-dimensional Landau levels, and then application of cadmium manganese telluride-based structure for terahertz microwave radiation-induced generation of pure spin current, generation of terahertz radiation pulses from spin waves, demonstration of new type of spin transistor, and if time permits, determination of enhancement of spin orbit field in collective spin excitations. Of course, we all know that spintronic is all about the spin because the spin is meant to be the basis of device operations. And therefore, an important branch of spintronic research is related to diluted magnetic semiconductors, which are mixed crystals of non-magnetic and magnetic semiconductors, with cadmium manganese telluride or gallium manganese arsenide being very well-known examples. And the reason for the interest in diluted magnetic semiconductors from the point of view of spintronic is because those materials are characterized by very strong enhancement of all spin-dependent properties. And that is due to the exchange interaction between localized spins of magnetic moment and spins of band carriers. And now, although 2,6 diluted magnetic semiconductors have been the first diluted magnetic semiconductors, their role recently is not that large as it could be, in my opinion. And one of the reasons for this is probably that they are not promising in the recent worldwide quest of room temperature ferromagnetic homogeneous semiconductor. But I believe that their role can be increased if only the technology would be improved of those structures, and especially if cadmium telluride-based two-dimensional nanostructure would be available, and even more so if electron beam lithography and focus ion beam lithography would be developed. So because those materials have some advantage over 3/5. First, they have enhanced excitonic effects. Manganese can be built into the lattice into substitutional positions up to 100%. So for instance, one can produce zinc blende manganese telluride, which does not exist in nature. So there is no problem with interstitial manganese. Also, the incorporation of isovalent manganese does not deteriorate excellent optical properties, and we already have seen this in the case of cadmium telluride quantum dots with manganese, mentioned at previous talk. And also, we believe that it should not lead to any critical reduction of the two-deck mobility. And I will return to this point. It is very advantage of this material is that they provide spin splitting engineering. And oops. And how one can grow those kind of structures? Of course, the best known and the most useful method is molecular beam epitaxy, and this is how we do how we grow out those structures in our Institute of Physics. And we have very small American company EPI now Vico MBE chamber with 6 ports, so we only can grow materials in these triangles from zinc telluride, cadmium telluride, manganese telluride, magnesium telluride. And actually tomorrow, on July 6th, will be 20th years anniversary of our first growth. And so we can only grow 2,6 tellurides, as I mentioned, and then we, of course, specialize in diluted magnetic semiconductors, and that is probably the reason for this invitation, which is, on the other hand, Warsaw's tradition, as you might know. And apart from normal quantum wells, superlattice quantum dots, we also grow more sophisticated structure like parabolic quantum wells, in-plane graded quantum wells, DMS nanowires, or the major subject of my talk, 2DEC. So just only one slide about the quantum dots, because we already have heard about them in the previous talk. Just only want to mention that a single manganese atom can be thought as an ultimate limit for information storage, and our colleagues from Warsaw University showed that the storage time on the single manganese ions can be as large as hundreds of microseconds. Now, so you can also cast those diluted magnetic semiconductors in the form of nanowires, and this can be done using the so-called vapor-liquid solid growth mechanism proposed by Wagner in 1964. And the idea is very simple. You just have to produce somehow a eutectic ball, which is liquid during the growth. And then you supply a flux of materials from which you want to grow your nanowires. In our case, is zinc manganese telluride. And then as soon as this nanoball is saturated with materials you want to supply, it just will keep growing, producing this nanowire. And that was not at all that obvious that manganese will build into the nanowire in this kind of growth, but we have demonstrated by various experiments. So this is the scanning electron microscopy of a forest of the nanowires. They always grow along 111B, typically preferentially direction. So independent on the substrate you use, the only thing which changes is the angle from the substrate. Now we have showed that it is in fact possible to incorporate up to 60% of manganese, and we have shown this by energy electron loss spectroscopy, resonant Raman scattering, studies of manganese internal transition. But of course, just to demonstrate that they are really diluted magnetic semiconductors, you have to prove that they have a very strong enhancement of spin properties. So this is an example of such a studies. So this is just a nanowire made of zinc manganese telluride with the shell to make those nanowires optically active, and you study the microphotoluminescence from the single nanowire, and you can clearly see the gigantic spin splitting, which is the very typical characteristic of diluted magnetic semiconductors, and the spin splitting scales with the concentration of manganese in the sample. So this is definitely proof of diluted magnetic semiconductor nanowires. And this is, we consider this a first step toward producing magnetic quantum dots and coupled quantum dots inside the nanowires. We have already shown that it is possible to produce cadmium telluride quantum dots by correlated spectroscopy. Now, moving to the main subject of my talk, to two-dimensional electron gas. As you might have noticed at this conference, that until recently, not including graphite, most of the research has been done on 2DEC. 2DEC was performed on gallium arsenide or silicon-based nanostructures because the technology is much well developed. And in respect of 2DEC, the probable advantages of our system is that they should probably have smaller charge metastable effects, which makes trouble in 3/5. They definitely have a larger intrinsic G factor. For instance, in cadmium telluride, G factor is minus 1.7, which is gives 4 times larger energy of Zeeman. Now, incorporation of isovalent manganese, as I already told you, this is as opposite to the case of manganese in gallium arsenide, where it is an acceptor, does not lead to any critical reduction of the mobility. And finally, the most important part, you can engineer effective G factor in these materials, and this G factor can be made both negative and positive, and as large as 500 G factor, effective G factor as large as 500 can be reached. And also the spin splitting can be also engineered so that you can have the crossing of spin up and spin down level at any required value of the magnetic field. You can think about using this for the studies of fractional quantum Hall effect, and there has been already a poster about this at this conference. And this comes because intrinsic G factor is negative. Exchange G factor, which is proportional to the Brillouin function, the modified Brillouin function, is temperature and field dependent. And then, if you apply a low temperature magnetic field, this part saturates, and then spin splitting is given by intrinsic G factor, so you can get spin splitting. Also, crossing of the spin up and spin down level. Also, the dependence on the spin splitting on magnetic field can be further engineered by non-even distribution of manganese in the gross direction. So you can, for instance, produce quantum wells made of cadmium, manganese, magnesium telluride, and produce required shape of the spin splitting. Also, we have already demonstrated, and by Jasia Roszyński, who is also at this conference, that those materials can be used for the studies of quantum Hall ferromagnet. It was already many years ago, where we have observed the splitting of the crossing of the Landau levels with different direction of the spin, so that if they are brought into the generous under quantum Hall effect, that this ferromagnetism of Carrier is produced. And the uniqueness of the system is that you don't need to apply in-plane magnetic field to produce this crossing. Now, there were many propositions of using diluted magnetic semiconductors if only appropriate samples would be available. One is from my colleague Boldi Żarianko and Mona Berciu from Notre Dame, and they have proposed to use superconductor on the top of the structure, and use type 2 superconductor, and use vortices to produce local texture in the diluted magnetic semiconductors because of its gigantic spin splitting. And then you can also further manipulate those local texture by sending currents through the superconductor. So I hope that I have convinced you that there is a need to produce such a structure. And before I go to show results, first I would like to mention that I've been chosen to be a speaker for the consortium of many institutions. One is, of course, our institute, where all the crystals has been grown, structures. Department of Physics, Regensburg University, Joffe Physico-Technical Institute in Russia, Solid State Institute in Haifa, Israel, and 3 institutions from France, Grenoble High Magnetic Field Laboratory group of Marek Potemski, École Normale Supérieure and University Paris 6 from Paris, and also Department of Physics and Astronomy, University of Missouri in US, and Department of Physics, University of York from UK. Let me start by letting you know how we produce such a two-dimensional structures. Of course, in gallium arsenide structure, you use gallium aluminum arsenide as a barrier. Here we use cadmium magnesium telluride as a barrier material. And we use iodine as a dopant because iodines like to segregate toward growing surface. We have typically, until now, we introduce, until very recent, until 2 days ago, we normals introduced iodine after the growth of the quantum well, so the donors will not go into the quantum well region. And now, in order to introduce manganese, you can do it either homogeneously or digitally. Digitally means that you just put some monolayers of cadmium manganese telluride into the quantum level region. And we perform our, of course, to get high mobility, you have to be careful about the purity. So you have to choose the best available materials. And also, please note that we use manganese and magnesium, which are produced in our institute by Professor Michalski group. And we grow our structure on 2-inch wafers. And we do it because not only they are inexpensive, flat and high quality, but also we want to, as I said, we want to develop E-beam and other forms of lithographies. And in order to produce good structures, we had to develop quite complicated buffer layers, including short period superlattices. So where are we now? It's presented on this view graph, where I have plotted results from for landmark samples in the gallium arsenide history. I did not put recent achievements of the mobility of roughly 40 millions, not to get too much disappointed, because you already can see that our structures are still far behind those produced by gallium arsenide people, and so actually we are more with our mobilities of 500,000, we are roughly in 1981 in comparison to, so there is still far way to go. But nevertheless, already this quality of the structure made a qualitative progress, because we could observe interaction-driven effects. So, for instance, fractional quantum Hall effect, and this has been measured by the group of Professor Marek Potemski. They have clearly showed that there is a well-developed 5/3 and 4/3 fractional quantum Hall effect state, and also by performing studies as a function of angle, so increasing the in-plane magnetic field. They have shown the typical experiment to show that this ground state is spin polarized, and which is of course expected because our materials have larger G factor than gallium arsenide. Now also, which is not typical for gallium arsenide, I was told, that in the case of our structure, it was possible to perform simultaneous measurements of optical and transport properties on the very same sample in the same time. So, and our colleagues from Grenoble have shown the enhancement of spin gap in the fully occupied two-dimensional Landau level, which was extracted from polarization-dependent photoluminescence, and for an arbitrary filling factor, which has been precisely determined by transport measurements. And they have explained this enhancement through many body interaction that has been driven by spin polarization of two-dimensional electron gas. And you could see this enhancement here, that whenever new factor, so filling factor becomes odd, you have the enhancement, large enhancement of the spin splitting. Oops. And having already reasonable quality quantum structure, we have started to make lower dimensional structure, and the first and the simplest one is of course quantum point contact, and there was also a nice poster at this conference about this. I only want to mention that we succeeded in producing quantum point contact by wet etching and e-beam lithography, but instead of flat plateaus in conductance, we have observed quasi-periodic oscillations, and due to the similarity of this observation to the similar observation gallium arsenide, in which quantum point contact had intentionally produced quantum dot, we interpreted our data that those oscillations are due to natural formation or self-formation of quantum dot due to the stronger electron-electron interaction and specific shape of the confining potential. Now, introducing manganese, as I was hoping for at the beginning, did not introduce too much problem. So if you don't put too much manganese, you still observe fractional quantum Hall effect states. And this, we know that we have manganese inside, not only because we have open, of course, cell, but also because we observe this nice beating pattern at low magnetic field, which are the indicative of the presence of the manganese, from which you can also determine the composition of the concentration of manganese. So, so means that manganese does not destroy this fragile fractional quantum Hall effect, and therefore I believe that one can use this system, taking advantage of crossing of spin up and spin down state at any required value of filling factor, including fractional, for the studies of fractional quantum Hall effect. And also I believe that somebody might come with some smart idea how to use this type of structure, for instance, to study fractional quantum Hall effect in double layers, for instance, with one quantum well being made of diluted magnetic semiconductors. So let me now move on to show you the already performed experiments. And this is first, let me start from terahertz microwave radiation induced zero bias generation of pure spin current. And our structure we used to, the spin splitting engineering was used to demonstrate mechanism of the efficient magnetic field induced conversion of them into electrical, spin polarized electrical current. And the idea comes from Sergei Ganichev, who was at this conference. And he noticed that in geotropic media, spin orbit interaction as asymmetric spin dependent term to electron scattering probability. And of course, this is due to the bulk and structure inversion asymmetry. So now, dependent on the sign of the K, the potential is different. So if you have, for instance, one direction of spin, then carriers are more scattered to the left. For the other, more to the right. And if you have balance between those two, so you have the same occupation, you should have the pileup of spins with no electrical current. But if you apply a magnetic field, for instance, in-plane magnetic field, so you produce the spin splitting, then you produce imbalance between those two currents, spin fluxes, sorry. And this can take place either on the excitation level, at the excitation level, and in this case, this excitation is polarization dependent given by this formula. If you measure current in the configuration, the magnetic field is in plane, and you rotate the polarization of your light. And then, through the absorption plus spin-dependent scattering. Now, also, if you already have these carriers at high energy, they relax to lower energy, and so you can have this generation of spin-polarized current, which is at the stage of relaxation, and the total current should be given by this formula. And so at low spin splitting, the current should be, electrical current should scale with the Zeeman splitting. And this is demonstrated in this view graph, showing the data for terahertz, so far infrared laser, and sub-terahertz carcinotron experiment. You can clearly see that there is very strong current induced in the configuration that I have shown before when you have the sample at very low temperature. Now, if you increase the temperature, this getting smaller, and that is because the exchange contribution has this temperature of manganese here, so the exchange G factor gets smaller, and the effect gets weaker. And in the case of low temperature, we have gigantic current because of the gigantic spin splitting. Now, if you raise the temperature much, much higher, then this is very small, and intrinsic G factor takes over, and you should have the change of the sign of the generated current. Now, in order to demonstrate, on the other hand, this contribution of the excitation mechanism, our colleagues from Regensburg performed the studies as a function of angle between the polarization axis and direction of the crystals, and they have shown that, in fact, this formula nicely describes experimental data. Now, next application of our structure with 2DEC, clear demonstration of terahertz radiation pulses from spin waves, which are excited in our material by efficient Raman generation process. And terahertz radiation from spin waves has been observed already in non-magnetic, antiferromagnetic, materials like nickel oxide. However, the claim that they have been observed also in gallium manganese arsenide was not that strong, because frequency range of observed transient did not match mode frequencies of the Okay, so now experiment has been done like this. They have used the log titanium sapphire laser. They have excited sample with circular polarized light, collected radiation by two parabolic mirror, and they detected the transient by free space electro-optic sampling with which was set in such a way so as to detect electrical field which is parallel to the magnetic field. And here is the result. For one sample, the transient, you can clearly see the terahertz radiation with for different magnetic field values, and the amplitude increases with the magnetic field, which you expect because you are raising the polarization of the spin. So you can introduce macroscopic spins, which takes this. So this is proportional to the macroscopic spin. Please note that in our experiment also, our experiment done by our colleagues, the power energy per pulse was much smaller, orders of magnitude smaller than in other cases, and that was because we could use high efficiency Raman generation mechanism, and also the possibility of using resonant Raman scattering, which was coinciding with real and sharp intermediate states, which was of course due to the high sample quality. And just this resonant character was used to prove that this really comes from 2DEC, not, for instance, from surface charge effects or from buffers, because the energy coincides with the energy of fundamental transitions. Now, in order to show the spin wave origin, one can use polarization selection rules, and it has been demonstrated by our colleagues that at zero magnetic field, where you don't have spin polarization, you do not observe those terahertz pulses. At linear polarization, you do not observe it because they can only couples to charge excitation, and you can only observe it in the presence of circular polarized light. And also radiated field has electrical field along the z-axis, so as we have set the detection system. And also the amplitude also reasonably well agrees with the theory. And now coming to the frequencies, at the beginning that was a puzzle why they have observed two frequencies. And of course they wanted to blame us for producing non-homogeneous samples, but that was of course not the case, because we have proven not only that samples are homogeneous by, for instance, quantum Hall effect measurements and optics, and so they had to come up with some other ideas, and the explanation is the following. As a result of laser pulse, the macroscopic electron spin starts to rotate in this in-plane magnetic field and emits terahertz radiation in the relaxation time. But also this spin is under the influence of manganese macroscopic spin, which also rotates around this magnetic field. So, and this manganese spin acts on S as a torque, and so this produces the splitting into two frequencies. And you can compare experimental data, which are for nu 2 given here and nu 1 given here. And our colleagues have had to solve numerically coupled equation of motion for S and M. And the numerical results are presented here, this nu 2 numerical and nu 1 numerical. But in order to bring this closer to the experiment, they also had to include in the fact that the experimental setup was working as a high-pass filter with cutoff frequency 0.3 terahertz. So they performed numerical filtering of this numerical data, and they brought this filtered nu 1 filtered closer to the frequency. So the agreement is quite reasonable. Now, the application of our structure for demonstrating a working principle of adiabatic spin transistor. And to put things in perspective, I will use the picture from the Zutik and Lee paper in Science. And the left-hand side, on the left-hand side, there is a conventional filter effect transistor where you can use electrical gate to control the flow from source to drain. In seminal data dots transistor, you use this voltage to control spin orbit field, in which electrons injected from ferromagnetic source to the two-dimensional channel will rotate. And now the state on is realized when the electron will come in parallel to the drain, and the state off will be realized if electron after traveling will rotate so that its spin is anti-parallel. But there were problems with this design. Because of not very efficient injection of spin, and also even more severe with the limited spin lifetime. So in the adiabatic transistor, which is proposed, is to use gradual change of the magnetic field to produce a helical magnetic field, and to so that electrons moving from source to drain will be able to adjust its direction of the spin, and that there will be no obstacle to the transport of the spin. Now, if you produce sudden change of the direction of the magnetic field, spin of electron cannot adjust to this sudden change. It will backscatter, and the resistance will be large. And this can be, as I already mentioned, of course, can be realized in our system, which is ideal, first because it has giant spin splitting, and also it has the best reported mobility in the case of diluted magnetic semiconductors. And now how you can produce this slowly varying helical field. You can use nanomagnets on the top from dysprosium. So you magnetize them, and then you produce spin helix. Now, how can you regulate? The first step is to use external magnetic field. Here is the results of micromagnetic simulation, and you can see Z and X components. If you apply external magnetic field so that the magnetic field in the center is compensated, you are left only with the X component, which suddenly, at this moment, it changes the sign. So you can regulate the adiabacity and to produce back reflection by applying external magnetic field. So the different samples had been used, both with manganese introduced digitally or homogeneously, and e-beam lithography sputtering liftoff. On the surface of samples, there were produced those stripes with the period from 0.5 up to 8 micrometers, and the stripes were half of the period white. Here is the scanning electron microscopy of one of the devices, and so those are those stripes. This is fake color. But here in the inset there is a configuration. So first you have to magnetize those stripes. You run at some angle to the normal, to high magnetic field up to 8 Tesla. You magnetize and you collect data while going back from +½ up to -½. And what you observe is then when you compare the two plots for unpatterned samples and sample with the pattern, you can see those two peaks, and roughly at ±50 millitesla. This is not the effect of one sample. As you can see, this is observed in other samples as well, actually in all samples. And now, in order to demonstrate that this is related to the actually to the spin in our structure, you can show this using normal trick. Namely, you can use the temperature dependence, so you can show that the amplitude scales with the Brillouin function, so the peaks disappear with the temperature. Now, in order to relate those peaks to stray field, you produce you rotate the field at which you magnetize your stripes, and they should, according to the micromagnetic simulation, be symmetric around 45. And you can see this. And also, they should move to higher field if you increase the period, the distance. Now, once again, how it works: the electron coming from the left to right without magnetic field adjusts its spin direction and can freely move to the right. So you are getting low resistance. If you produce this degeneracy points electron going from source to drain comes to the moment when it would have to change suddenly its direction, and therefore this leads to the Landau-Zinner transition between speed up and speed down levels, and also leads to the reflection, so to the high resistivity region. But this has been also confirmed by by calculations from the group of Professor Richter and the first author Henry Sarikowski, who is at the audience. So in case of questions, you can ask him. So they have considered spin-dependent magnetoconductance through magnetically modulated waveguide using Landau-Büttiker formula, 2 levels of approximation ballistic model Landau-Zinner theory, and large-scale numerics, and they have done it both for ballistic and disorder system. I only want to show you that that theory describe experiment data quite well. So this is experiment, this is theory, and please note that both for ballistic and disorder system, those data are quite well reproduced. Also, they have performed calculations versus angle, and again, here's the experiment for different for sample B and C, and here's the this angle dependent. Now, just since I don't have too much time, I only want to tell you that our structure were used by our French colleagues to show spin orbit field for intra-subband spin wave excitations, and what was predicted some time ago and recently shown in the case of inter-subband spin plasmons, that those excitations are intrinsically protected from the Diakonov-Perel decoherence. However, and also that the spin orbit field acting on this collective spin excitation are drastically enhanced. And so our system happens to be convenient because in our system it was possible to observe in the same sample experimentally both spin orbit field at single and collective excitation level. Just so they have used inelastic like scattering experiment, and please note that they have the peak from spin flip waves and also single particle excitation. This is very sharp, so means that you have single collective spin orbit field, and this is so these two shoulders represent the spread in the K. So they have used, I don't have time to go into details, but they have performed the studies as a function of Q, which was for different data collected for different angles, and also they have shown that from the studies as a function of angle between the polarization of the light and crystallographic axis, they can determine the collective Rashba, so spin structure inversion asymmetry and bulk inversion asymmetry, Drescher-Haus linear terms. Assume in the model they have assumed the same as they in the previous paper, that the spin flip wave can be treated as a macroscopic object subject to the collective spin excitation, proportional to this excitation. So using this formula, they were able to reproduce data quite well. Also, in order to determine the alpha and beta at single particle level, they had to produce some calculation of polarizability, but with this number of parameters, they were able to, this type of parameter, they were able to describe data reasonably well. And from the point of view of crystal grower, it's always good to hear that our samples are good. And they said that this disorder parameter in our sample was few times better than in any previous sample, so confirming that this quality of the sample was really very good. So from these studies, they have determined, as I said, the enhancement of the spin orbit field for this spin wave excitation. And so in conclusions, I believe that our results created some progress, and I hope that those structures can be used in the future for many interesting experiments. For instance, the physics of fractional quantum Hall ferromagnet, spin texture system, including this that I have shown you, superconductor DMS. Also, those structures can definitely be used for electrically defined magnetic quantum dots. So Pavel Havrak will be probably happy to have such a structure produced. Also, one can think, proposed by Jurek Wróbel and co-authors, 3-terminal ballistic nanojunction spin filters and so on. So if you would have any idea how to use our high-quality 2DEX structure, please come to us, and we'll be eager to collaborate. Thank you very much for your attention.
Thank you very much for a very nice talk. The forum is now open for questions and comments. Questions, comments? People up in the back who I can hardly see. Yes, right here, please.
First, my question is about high mobility structures. What limits your mobility? And you also mentioned you are planning to increase it. So how much you think you'll be able to increase?
That's, of course, a very good question. But in order to answer for this question, you would have to first grow better structures. But unfortunately, one of the problems is that the purity of the materials you can buy now, cadmium and tellurium, is 7N. Okay? In gallium arsenide, they buy 9N. So we already are 2 orders of magnitude lower. Okay? So we might be stuck by the purity by the purity of the elements unless we will be able to buy. I was not able to buy pure materials, but I am also 100% sure that we can improve just by improving the growth, because there is no, I say, obvious limit. If you introduce too much manganese, that's of course you will have magnetic scattering, and you will which will be killed by high magnetic field. But you will also have scattering due to mixed crystal. But I still believe, and also the strange thing is also in our case that although we have not very high transport mobility, which is, let's say, 500,000, but our quantum lifetime is more than expected for that mobility. So actually, in high magnetic field, our samples looks much better than you would expect based on the transport mobility. So,
are there other questions or comments? Yes, please.
Other donors in the heterostructure behaves in the same way like in aluminium-gallium arsenide. So they are frozen at helium temperature, or they mobile. I mean, when you apply gate voltage, electrons from donors disappear.
It's like this. There are not too many experiments performed with the gates yet. So actually, we had this paper which I have shown about this quantum Hall ferromagnetic studies, quantum Hall ferromagnet. We had a gate, and we were able to change concentration by a factor of 3. And at this conference, Leonid Rokinson showed me also result because I gave him our samples so that he can also move. So we can control electrically. But we also can control by illumination. So for instance, so it is kind of similar to gallium arsenide. So if we illuminate our sample, we can increase a bit of concentration, but also we can increase mobility. And this is important. So for the very highest, for the highest mobility, we use also in illumination of sample.
One more question, comment? Okay, if not, then let's thank Tomasz for a very nice talk.